we're looking at Euclid division lemma in divisibility. So we are using Euclid division lemma in dividing stuff and representation and all of those. So the concept is quite weird, but when you get to use it, then you'll understand how the concept works and you appreciate it better, right? So let's start off with looking at 107 and 25. As 107 is greater than 25, I can always write these two numbers as the following. First I'll divide. So this goes by 4 and then the remainder is 7. So I can write 107 as 25 into the quotient plus the remainder, is it not? So a random number can be written as another random number into quotient plus the remainder. So A, B, Q and R. These are the variables that we will use. So the next question is, instead of this, I would like to use 43 and 6. So 43 is greater than 6. So we are looking at 43, 6 sevens are 42 and the remainder is 1. So we are looking at 43 being equal to 6 into 7 plus 1. That is A is equal to B into Q plus R. Right? So this is the pattern which we are looking at. Next, instead of this, I would like to have 45. Now we are looking at 45 being greater than 10. So I'll divide 45 with 10. 4 is 40 and 5 is the remainder. So I can write 45, the bigger number as the smaller number, into quotient plus the remainder. Again, we are going to use A as your variable, B as another variable, Q and R. And here the remainder was 5. Right? So now, the actual statement of Euclid division lemma. Given to any positive integer A and B, there exists a unique integer Q and R satisfying the below equation. Okay, so you're looking at the equation over here, right? So any big number can be written as small number into the quotient plus the remainder, where the remainder is always greater than 0 but lesser than B. So this is a condition, right? This is a condition. So let's understand this condition a bit detailedly, because understanding this is important. I know it's easy to write, but why is it so? Let's understand the pattern, and that's how they wrote the lemma at the first place, right? We'll understand how they came to a conclusion. Okay, so let's start off by understanding this particular, what is that we are writing over there and why is that we are writing over there. So to do so, we consider a set of numbers and then we are looking at the remainder when we divide this set of numbers with 5. So the remainder of 5. So when you are dividing 11, the remainder is 1, 2, 3, 4. Is it not? 14 divided by 5 is, the remainder is 4. And this is 0, 1, 2, 3. Do it along with me in your head. 4, 0. Say I was able to write 5. This is 1, 2, 3, 4, and this is 0, and this is 1. So what is the pattern you are looking at? Well, the remainder is varying from 1 to 4. 1 to 4. It's certainly starting from 0, 1 to 4. 0 to 4, 0 to 4, my bad. 0 to 4, 0 to 4. It's certainly starting from 0 and certainly ending at 4. This is the pattern which we are looking at. That is, when we divide any number with 5, the remainder has to be lesser than or equal to 0. Greater than or equal to 0. Right? It can be equal to 0. And it can be greater but lesser than 5. Is it not? So that's what we are looking at. It's lesser than 5. Next one. When we are dividing with 7, 11 divided by 7 is 4. 12 is 5, 6, and then 14 is 0, 15, 16, 17, 18, 19, 20, 21, right? 21 divided by 7, remainder is 0. 1, 22, 23, 24, 25, 26, so on and so forth. So here the pattern is what? 1 to 6, 1 to 6 certainly starts with, sorry, not 1 again, 0 to 6, 0 to 6 certainly starts with 0, certainly ends with 6. So here the remainder when we divide with 7 is between 0 to 6, including 0 but excluding 7, right? The remainder starts with 0, ends with 6, is it not? So 0 less than or equal to, the remainder is greater than or equal to 0 but certainly lesser than 7, right? This will be your statement. Instead of writing the remainder will be 0, 1, 2, 3, 4, 5, 6, we are writing this fancy way. That's it. It's just a fancy way of telling, okay, remainder starts from there to there. That's it, right? So same thing, let's have a look at it using Python. So let's program this particular scenario and we'll have a visual representation of whatever we just did now. So I am dividing starting from 250 to 300, right? And the divisor is, let me make it a small number now, 3. Okay, so let's have a look. So let us observe what is that we are looking at. Yeah. Now, along the x-axis, what is that we are looking at? Whenever you look at a graph, the first thing you have to do is look at x and y-axis and the label and everything. I didn't do the label, I didn't type it, but I'll be writing it over here. So the heading is divisibility with, I think 4, 3, what was it? 3, right? 4, 3. Okay, so I'm dividing things with 3. So along the x-axis we have the dividend starting from 250 to 299, and the remainder is running along the y-axis starting from 0 to, well, in this case we don't need till 16, but anyways it's there. So when I divide 250 with 3, I get a remainder of 1. 251 I get a remainder of 2. 252 I get a remainder of 0. So let's verify this. How to verify? Since it's showing that 252 is getting divided by 3 with a remainder 0, so my quotient should be just a whole number, 84. But if I take any other number like 253 divided by 3, since it's showing that the remainder is 1, so you have the quotient to be a decimal form. It will be in decimal form. Okay, in this case if we divide it to using your decimals and all that, you will get this. Is it not? It shows that the remainder is not equal to 1. Clearly shows that remainder is not equal to 1. Then you have 254 divided by 3, right? 254, is it not? So it's over here and the remainder is 2. 254, the remainder is 2. So the next thing you need to observe is, right? So now we concluded that whatever is happening over here is true and it's proper. My coding is proper, no issues. So the next observation is that this is the line for 3. You can see that remainder is never 3. It's lesser than 3, equal to 0, greater than 0, but never over here. Never in this region as of now. It's not there. Okay. So the remainder is, when I divide with 3, right, the remainder will always be it can be equal to 0, greater than 0, but it's always lesser than 3. So instead of telling reminder is 0, if not 1, if not 2, we are just writing this fancy way. That's it, nothing else. It's just a fancy representation. Okay, right? So let's change the number to some big fat number. Let me change it to 15. Right? So let's look at what the output will be. I'm sure you guys would have guessed it. So here we are looking at reminder from 0 till 14. Make sense? So here we're looking at divisibility with 15, right? So we are dividing with 15. Now when we divide 250 with 15, I get a remainder of 10. If I divide 255 with 15, I get a remainder of 0. Let's verify this. Clear it. 255 divided by 15. Right? It is divisible. That's why you're getting a proper number. Any other number like 262 divided by 15? Clearly not. The remainder is not clearly equal to 0. Is it not? Right? So the programming looks to be good. So again, I'm taking the line 15, drawing a horizontal line. So clearly the reminders are not crossing 15. So I can conclude this. The remainder over here is always greater than or equal to 0, but lesser than 15. Make sense? Right? So this is the whole Euclid division lemma. So to conclude, we will be writing this. I have set of divisor, right? These are divisors, and we have to write the respective remainder for this, right? You have to write the respective reminders when we are dividing with all of these numbers. So please pause the video and write the remainder. So what I want you guys to write is, if you're not getting it, so remainder always is greater than or equal to 0 but lesser than 6. When you are dividing with 6, it is so. Same thing, right, for everything else. The remainder is always blah 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 blah. Continue. Pause. Right, here when you're dividing with 1 to 1, the remainder is between 0 and 1 to 1. That is, remainder is greater than or equal to 0 but less than 1 to 1. Remainder is greater than or equal to 0 but lesser than 33. Here the remainder is greater than or equal to 0 but lesser than 11. Here the remainder is greater than or equal to 0 but lesser than 7. Right? It's never equal to the divisor. Remember that. Remainder is greater than or equal to 0 but lesser than 9. Right? So indirectly we are telling the remainder can be 0, 1, 2 till 8. Is it not? Make sense, right? When we are dividing with 9, that's your remainder. That's it.